Now, in this lesson, we are going to look at some of the experimental designs. First, we will look at randomized complete block design, and we will look at two-wave or two-factor ANOVA, and Latin square design, and nested design. Before we go into the design, we have a few terms which you need to know. First is factor. I have mentioned before when we were learning about one-way ANOVA. Now, a factor is any aspect of the experimental condition which affects the response variable value from an experiment. For example, as a chemist, you are doing some experiment to generate a product. Therefore, you need the value of pH. You have to fix certain value of pH and certain temperature and the concentration of reactants and so on. So those are called factors which affect the response variable. And the response for you is the weight of the compound that you are getting. In the example of dependence of fluorescence signal on the conditions under which a solution is stored, the factor of interest was the storage condition. So that was an example last time when we were studying one-way ANOVA. Now it is called a control factor. Means that it can be changed by the experimenter. Now, in the example in which salt from different parts of a barrel was tested for purity, the factor of interest was the part of the barrel from which the salt was taken. And it was chosen at random. Now, that is called uncontrolled factor, the part of the barrel. That is an uncontrolled factor. Now, both of these examples are qualitative. The factors are qualitative. That means that their possible values cannot be arranged in numerical order. So we have two examples of qualitative factor. Now, quantitative factor, on the other hand, is a factor for which the possible value can be arranged in numerical order. Now, for example, temperature, if you do the experiment at 5 degrees, 10 degrees, 15 degrees, 20 degrees, so we have 4 levels of temperature, for example. Now, there are other factors that affect an experiment. For example, going back to the time when we were studying one-way ANOVA, we look at the experiment, the fluorescence experiment, how the fluorescence was affected by storage condition. Now, even though we study storage condition, other factors, for example, temperature, fluorimeter used for the measurement, people who made the measurement, the day on which measurements were made, also may affect the result of the experiment. So, what is experimental design? Experimental design is used to describe the stages of identifying the factors which may affect the result of an experiment and designing the experiment so that the effects of the uncontrolled factors are minimized and using statistical analysis to separate the effects of various factors involved. Now, an assumption of ANOVA is that uncontrolled variation is random. Uncontrolled factors can be temperature, pressure, or deterioration of instruments, and those can produce a trend in results. For example, if you want to compare the effect of a single factor at 3 different levels, or in general, we call 3 treatments, A, B, and C, and we require 4 replicate measurements. Instead of making 4 measurements for A, followed by 4 for B, and so on, we made 12 measurements in random manner. And this is decided by using random number method. So we are trying to do randomization. Now, one design called completely randomized design, in short we call CRD. This is a kind of design where we use one-way ANOVA to analyze the result. Now, for completely randomized design, each of the treatment assign a number for each replicate. Let's say, for example, A, B, C. Okay, and we assign number to it: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now, to randomize, you enter the random number table at any point and read off pairs of digits and repeat this way. Now, if the sequence that you read is the numbers that you got from random number table is 0, 2, 1, 10, 4, 3, 11, 1, 12, 6, 8, 7, 9, 5, then measurements will be made at the different levels in the following order. So when you conduct your experiment, you will be doing in this order. That means 2 is here, right? So you will do treatment A. Then 10, where is 10? 10 is here, right? It's treatment C. So you conduct this experiment. And then 4 is here. It's a treatment A. So you will do A. Then the fourth number here is 03. 03 is treatment A again. So you will do A. And you continue. 11 is treatment C. So you do treatment C. So you will do the experiment in this order. So randomizing this way will allow us to make sure that errors at level A, B, and C due to uncontrolled factor are at random. Now you may say, how do I get all these random numbers? You can generate it using SPSS, and you can get it from random number tables. Now that is a complete randomization. Yeah, we have 12 experiments that we need to conduct. Yeah, with 3 different treatments. So there are 12 measurements that we need to make. Now there is a disadvantage of that complete randomization because it fails to take advantage of any natural subdivisions in the experimental materials. Example, all the 12 measurements in the previous example could not be made on the same day, but had to be divided into 4 consecutive days. So, let's say these are the 12 measurements that you need to make. You cannot finish in one day, yeah? So you need 4 days to do it. So we can apply blocking method. Okay? Let's say, for example, if we were to use the same order as before, day 1 will be doing measurement from treatment A, treatment C, then treatment A. Day 2 will be making from treatment A, treatment C, treatment A. Day 3, treatment C, treatment B, and B. And day 4, B, C, B. Now you notice that treatment A happens to occur on the first 2 days, day 1 and day 2 only. Then treatment B occurs on day 3 and day 4 only. There seems to be, if let's say, there seems to be any difference between A and B, then will it be possible for us to tell the difference? Or is it because the measurement was done on different days, like day 1, day 2, day 3, day 4? So the better way is to use a randomized complete blot design, whereby each treatment appear on each day. Say we have 3 treatments, right? A, B, C, right? So each treatment appear once a day. Then how does randomization come in then? This order can be randomized. For example, A, C, B. We don't have to start from A, B, C. Yeah. So the order of treatment can be randomized each day. And each treatment is done once each day. So day 1, we do A, C, B. Day 2, we do A in this order, A, B, C. Day 3, we do C, B, A. Day 4, C, A, B. So this is a better design, and this design is called randomized complete blot design. And each day is a block, okay? So when this happens, now we have 2 factors. One factor is the treatment, and another one is the day. Yeah? The block here is the day. Now what is a block then? A block is a group which contains one measurement for each treatment. Originally, this word treatment refers to an area in a field in agriculture where a treatment of fertilizer A, fertilizer B, fertilizer C, or pesticide A, pesticide B, pesticide C are used. That's why it's called treatment. You know? In this case, the measurement on each day form a block. Block, in this sense, is an extension of the term pair. Remember, we have pair design. We have t-test, right? Pair t-test. Now, pair t-test, we can only compare 2 means. Now, if you have 3 or more, then you cannot use pair t-test. So we use this ANOVA, and the block here is an extension of that pair. Now, this completely randomized blot design has advantages because it takes account of variation that may arise from different days involved in the experiment, and it is more sensitive than the unblocked analysis. Now, for randomized complete blot design RCBD, we use two-way ANOVA to analyze the data. There are 2 factors involved here. There is treatment and day. But actually, only treatment is of interest to us. Each measurement is classified according to 2 factors. So total variation is partitioned into variation due to the treatment, variation due to the block, and unknown or random variation. So In symbol form, the total sum of squares, which measures total variation, is equals to sum of square due to the treatment plus sum of square due to the block plus sum of square due to the error or unknown variation. Now please refer back to the one-way ANOVA and you compare. For one-way ANOVA, the total variation is only divided or partitioned into variation due to treatment here and unknown variation or random variation. We do not have variation due to the block. Now, to decide whether treatments produce significantly different results between treatment variation is compared with random variations. The sensitivity of the experiment depends on the size of the random variation. The smaller the random variation, the smaller the difference between treatments which can be detected. Now, in an arm block experiment, that is the completely randomized experiment, random variation will be larger since it will include a contribution due to day-to-day variation. And consequently, the sensitivity of the experiment will be reduced. Now, this is the general form of the data. We have the treatment, 1, 2, 3, and so on. This is a J treatment, and total number of treatment is T, and block. So we have block 1, 2, 3, and so on. This is the I treatment, and this is the total number of blocks. And we use the total here. Total for treatment number 1, you add up these data and give you T dot 1. Now each of these is called Xij, where I refers to the treatment and J refers to the block. Now, this is a two-way ANOVA calculation. Two-way ANOVA without interaction calculation. We'll learn the interaction later on. So this looks very similar to the one-way ANOVA table, except that we have between blocks now. Okay? So the source of variation between treatment, between blocks, and residual, the error, and the total. And these are the formulas that are being used. And these are the degrees of freedom. So you need to know how to build this two-way ANOVA table. And this is the mean square. And of course, from this mean square, then you can compute the F statistic value. So to find the SSE error, total sum of square is equals to sum of square due to the treatment plus sum of square due to the blocks plus SS sum of square due to error. So sum of square due to error is the total sum of square minus SSTR stands for treatment minus SS due to the blocks. Now we look at one example. Example is by looking at the example, it will be easier for you to understand. In an experiment to compare the percentage efficiency of differentiating agents in extracting metal ions from aqueous solution, the following results were obtained. Is there any difference between the efficiency of different chelating agents? So we have here chelating agents, 4 different types of chelating agents, A, B, C, D. And this experiment was conducted in 3 days. Day 1, we have the 4 chelating agents. Similarly, day 2 and day 3. So we have 4 treatments, 3 blocks. What is the response variable? It is the percentage efficiency of the chelating agent. Yes. So there are 2 factors here. One is the type of chelating agent. The other one is the day. And the day here is a block. Now notice for chelating agent A, day 1, we only conduct 1 replicate. That's why this is called without replication. Now, if you are using calculator, it will be easier for us to subtract 80 from each of the value because they are all near 80. All the values are close to that. So that we deal with a smaller number in computation here. So for day 1, block 1, yeah. So the total is 4 plus 0 plus 3 minus 1. So T1 dot is equals to 6. Total of block 1. Similarly, when you add this way, total of block 2 is -5. And you add this way, total of block 3 is -1. So when you square this, block total, 6, 6, 36, 5, 5, 25, -1 times -1 is 1. Now, treatment total, yeah. Treatment A give you total of 6. Treatment B, -5. Treatment C, 3 plus 0 give you 3. -1 plus -1 plus -2 give you -4. So those are, you square it, 16, square it, 9, square it, 25, square it, 36. So the sum of total square is 86. And the sum of total square here is 62. So we can use this in our computation here. Okay, 86, 62 here. So the source of variation between treatment and between blocks the sum of squares. Follow the formula so you can get this value. Between block, the sum of squares. So residual here, the total, total minus this give you this. The degree of freedom, there are 4 treatments, so degree of freedom is 4 minus 1 is 3. They are 3 days, so 3 minus 1 is 2. And the total, they are 12. 12 minus 1 is 11. So to get the degree of freedom for the error or residual, 11 minus 3 minus 2 give you 6. Now mean square, you take this, divide by the degree of freedom, give you 9.5 and so on. 15.5 divided by 2 give you this. This divided by this give you this. So this is the MSE error. So to get the F statistic value, you take this divided by this. MS between treatment divided by this give you this. This MS between block divided by this MS error give you this. Yeah. So the test for significance between treatment, we need the null hypothesis and the alternative hypothesis. So null hypothesis, no differences among the treatment means. And alternative hypothesis, there is a difference among the treatment means. And with this test statistic value, MS for treatment divided by MS error, they give you 5.83. And the critical value, you look up in the F table, F of 0.05, number of treatment minus 1, 3, T minus 1 times B minus 1 give you 6, and that is 4.76. Or you look up the degree of freedom for error here. This is degree of freedom is 6. They give you 6 here. So this is 4.76. Compare your test statistic value with the critical value, and then you make decisions. So since f equals to 5.83, which is bigger than the critical f value of 4.76, we reject the null hypothesis. So the null hypothesis, no differences among treatment means, is rejected. We accept the alternative that there is a difference among the treatment means. So our conclusion is there is a significant difference in the chelating agent's efficiency at 5% level. Of course, if you are using SPSS program where they give you the p-value, then you can make decision using the p-value. Since p-value is 0.03, which is less than alpha of 0.05, we reject the null hypothesis. Now, even though between treatment is our main interest, we can also test for the significance between the blocks just to see whether the blocks make any significant difference or not. So the null hypothesis is no differences among the block means. Alternative, there is a difference among the block means. The test statistic value, f equals to ms. Oh, okay. This is B, yeah? This is not T, it's a block. Yeah? So correct that is ms of the block divided MSE, and they give you 4.76. The critical value, the number of blocks, the number of block minus 1, correct. The number of block minus 1, so we have 3 days, minus 1 becomes 2, and the degree of freedom for error is 6. So look up the F table, it gives you 5.143. So we can make a decision, compare 4.76, it is less than the critical value. So the calculated F value is less than the critical F value of 5.143. So we accept the null hypothesis and conclude that there are no differences among the block means. Now, if you are to run SPSS, this is the ANOVA table. Day is the block, the agent, chelating agent, and the error, the sum of squares, and the total. Okay. So the significance here give you the compare with the alpha, and this is the F value for the day and for the day and for the agent, 5.831. Now, if you look at the alpha here, significance 0.058, 0.033, So this one is bigger than alpha, so it shows that there is no significant difference among the days. This one is less than alpha, so we say there is significant difference among the chelating agents. In terms of the efficiency. Now, the advantage of blocking. Even though there is no significant difference between days, the p-value equals to 0.06 or 0.058, the between block mean square is considerably larger than the residual mean square. And had the experiment not been blocked, so that these two effects were combined in the estimate of experimental error, the experiment would probably have been unable to detect whether different treatment gave significantly different results. For example, if it is not blocked, then our analysis of the experimental data, we will be using one-way ANOVA. And observe that in one-way ANOVA, the sum of squares between groups, between treatment is here. Now we only have the error here. So the error here is the total from block and from the unexplained. So this becomes very big. See? So MSE, MS is MSW, it becomes big. So when this divided by this, it gives you the F value, which is lower than the critical value. And when F value, calculated value, is lower than the critical value, we cannot reject the null hypothesis of no difference. So you observe that the conclusion will be that there is no significant difference in the efficiency of the chelating agents. So one-way ANOVA is not suitable to be applied here. This is the exercise for you, whereby there are 4 standard solutions prepared, each containing calculated 16.00% by way of chloride. So try to test whether there are significant differences between concentration of chloride in the different solutions and the concentration of chloride obtained by different methods. Use the same formula for calculation. I give you the final answer here for you to compare. Now, Latin square design is is a further steps from the completely randomized blot design. Now, an uncontrollable factor for the example that we were looking at is that the time of the day where the experiment or the measurement was made was not taken into account. So, for example, systematic variation during the day, deterioration of the solution that you make in the morning, after that 9 o'clock, 10 o'clock, 11, 12, as time goes on, the solution may deteriorate. So time of the day at which you do the experiment is important as well. Or there is one directional change in laboratory temperature could produce a trend in the results also, where in the morning is cooler and in the afternoon is hotter. So Latin square design, observe the difference here. This is a Latin square design compared to the complete randomized complete blot design just now. You see that, observe that C is concentrated. The treatment C is concentrated in the beginning of the day. So in Latin square design, each treatment appears once in each row and once in each column. So instead of 2 appearing early in the day, we make sure that there is only 1 appearing in the early part of the day and the midday and the end of the day. So now the total sum of squares, the total variation, is partitioned into between treatment variation, between day variation, and this is the additional one, between time of the day variation and unknown variation or random variation. Now note that for Latin square design, column is one blocking factor Rows is another blocking factor. And the letters designate the treatment. If the square is greater than 3 times 3, there are more than one possible design, and one of the design can be chosen at random. So what's the disadvantage of Latin square design? It requires equal number of blocks and treatments. Now, nested and cross-classified design. The randomized block design is known as cross-classified because a measurement is made for each possible combination of different levels of factors. If a sample or standard solution is sent to each of the 3 labs, and in each lab, the sample is analyzed by 2 different technicians, this kind of design is called nested design or hierarchical design. Not all possible combinations of experimental design are used. For example, the technicians do not make measurements in the lab other than their own. So nested design looks this way. For example, standard solution is sent to 3 laboratories, and in lab 1 there are 2 technicians, in lab 2 there are 2 technicians, in lab 3 there are 2 technicians. So this is called nested design. So that's the end of this lecture.